Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Special Theory of Relativity from paper Classical Mechanics. So students, let us see what we are going to learn in this module. In this module, we will learn about the contravariant and covariant vectors and their transformation properties. Secondly, we will learn to derive relativistic kinematic relations between energy, momentum and scattering angles for two particle scattering processes. In Newtonian world, view space and time are independent absolute entities. In Newtonian worldview, space and time are independent absolute entities. The Newton's laws of motion are invariant under Galilean transformations when we go from one inertial frame to another which is moving with a uniform velocity with respect to one another. The Galilean transformations are given by r prime equals r minus vt and t primes equals g. R and r prime are the position vectors measured in the unprimed and primed inertial frames which are moving with a relative velocity v with respect to each other. In Newtonian frame, work time is independent of the reference frame. Maxwell's equations of electromagnetism, however, do not satisfy the principle of Galilean relativity. Maxwell's equations predicted that the speed of light in vacuum is a universal constant and is equal to c. If this is true in one coordinate system, it clearly will not be true in another coordinate system which is moving with a uniform velocity and defined by the Galilean transformations. The pioneering attempts for the resolution of the problem of relativity in electrodynamics and mechanics were made by Lorentz and Poincare. The problem was finally resolved by Einstein in 1905 in the form of postulates of special theory of relativity, which states, first, the laws of physics are invariant in all inertial frames. Secondly, the velocity of light in free space is a universal constant which is independent of the frame of reference. In Einstein's worldview, space and time are still absolute entities, but they are not independent. They form a four-dimensional Minkowski space. Let us begin with the Lorentz transformation. Lorentz transformations have the fundamental property of keeping the velocity of light constant in all inertial frames, which means that ds square is equal to c square dt square minus gx square, which remains invariant under the transformations x prime is equal to x minus vt divided by square root of 1 minus v square by c square. This is equal to gamma times x minus beta ct. Y prime is equal to y and z prime is equal to z. T prime will be equal to t minus vx by c square divided by square root of 1 minus v square by c square, which is equal to gamma times t minus beta by c into x. Here, gamma is equal to 1 by square root of 1 minus v square by c square and beta is equal to v by c. The Lorentz transformation is thus a transformation from one system of spacetime coordinates x mu to another system x prime mu such that x prime mu equals lambda mu nu x nu plus alpha mu, where alpha mu and lambda mu nu are constants. We define the coordinates alpha mu in a four-dimensional Minkowski space as x mu is equal to x naught comma x. Let us say it as equation 25.4. We also distinguish the upper indices which are the contravariant and the lower covariant indices as x mu is equal to x naught minus x. Let us number it as equation 25.5, which can be obtained from the contravariant coordinates by transformation through the matrix G mu nu, namely covariant x mu is equal to covariant G mu nu into contravariant x nu. Say equation 25.6. Now, the scalar product, which is contravariant x mu with covariant x mu, is equal to x naught square minus x square, which is equal to G mu nu into contravariant x nu into contravariant x gamma. Let us say it as equation 25.7. In terms of the matrix tensor, ds square is equal to covariant G mu nu into d contravariant x mu into contravariant x nu. Say it equation 25.8. The matrix tensor is defined as G mu nu is equal to the first row elements being 1 0 0 0, second row being 0 minus 1 0 0, third row being 0 0 minus 1 0, and the last row being 0 0 0 minus 1. That is, G mu nu is equal to plus 1 for mu is equal to nu is equal to 0, and is equal to minus 1 for mu is equal to nu is equal to 1 2 3. It is equal to minus 1 for mu not equal to nu. Lorentz transformation takes gx mu to dx prime mu, given by dx prime mu is equal to lambda mu nu into dx nu. ds prime square is equal to g mu nu into dx prime mu into dx prime nu, which is equal to g mu nu into lambda mu alpha into lambda nu beta into dx alpha into dx beta, which is equal to ds square and is equal to g alpha beta dx alpha into dx beta. The Lorentz transformations thus have the fundamental property lambda mu alpha into lambda nu beta into g mu nu is equal to g alpha beta. The first property is determinant of g is equal to minus 1. Second property being g inverse is equal to g transpose, which is equal to g. Third is g alpha beta is equal to g alpha beta. Fourth, g mu alpha into g alpha nu is equal to delta nu mu. We now define a 4-vector v mu, any quantity that transforms like dx mu. That is, v mu transforms to v prime mu, which is equal to lambda mu nu into v nu. Equation 25.12. When the coordinate system is transformed by x mu tends to x prime mu, which is equal to lambda mu nu x nu, let us say it as equation 25.13, v mu like x mu is called a contravariant 4 order to distinguish it from the covariant vector v mu, which transforms as v mu transforms to v mu prime, which is equal to lambda nu mu into v nu. Equation 25.14, where lambda nu mu is equal to the covariant component g mu alpha into the contravariant component g nu beta into lambda alpha beta. Let us say it as equation 25.15. The scalar product of a contravariant vector with a covariant vector is invariant under Lorentz transformations. That is, the covariant u prime mu into the contravariant v prime mu is equal to the covariant g mu is equal to the contravariant g mu alpha into covariant u mu prime into covariant v alpha prime. This is equal to g mu contravariant g mu alpha into lambda nu mu into lambda beta alpha into the covariant u nu into v beta. This is equal to g contravariant g nu beta into the covariant u nu into v beta. This is equal to u nu into the covariant u nu into the contravariant v nu prime. Let us number it as equation 16. We define a 4-gradient operator. Del by del x mu is equal to del by del x naught comma minus del operator. This is equal to del by del x naught comma minus del by del x1 comma minus del by del x2 comma minus del by del x3. The partial derivative with respect to the transformed coordinates x prime mu is given by del by del x prime mu is equal to del x nu by del x prime mu into del by del x nu. Number it as equation 25.18, and we see that differentiation with respect to contravariant component of the coordinate vector transforms as a component of a covariant vector operator. That is, the contravariant del mu is equal to the del by del of covariant x mu, which is equal to del by del x naught, del by del of covariant x naught, comma minus del operator. The covariant del mu is equal to del by del of contravariant x mu, which is equal to del by del x naught, comma del operator. The divergence of a 4-vector, that is contravariant v mu, is invariant. That is, the contravariant component del mu into the covariant component v mu is equal to the covariant component del mu into the contravariant component v mu, which is equal to del of the contravariant v naught divided by del of covariant component x naught plus del operator dot del operator. The 4-dimensional Laplace operator is written as D-Lambert's operator, which is equal to del mu into the covariant del mu into contravariant del mu is equal to del square by del x naught square minus del operator square. Let us now discuss the particle dynamics. We consider a particle moving in a force field. We define the relativistic force F mu acting on a particle with coordinate x mu of tau by F mu is equal to m into d2x mu by d tau square. Let us say it equation 25.22, where d tau is the proper time. D tau is equal to square root of dt square minus dx square. And we have put c is equal to 1 in the natural units. Clearly knowing F mu, we can compute the motion of the particle. The relativistic form given by equation 25.22 of Newton's second law allows us to define an energy momentum 4-vector. P mu is equal to m into dx mu by d tau, and the second law can be written as dp mu by d tau is equal to f mu. Let us call them equations 25.23 and 24 respectively. We have d tau is equal to square root of dt square minus dx square, which is equal to square root of 1 minus v square dt, where v is equal to dx by dt. The space components of contravariant component p mu forms the momentum vector p is equal to m into dx by d tau, which is equal to m into dx by dt into dt by d tau, which is equal to m into v into gamma. And the time component is the energy, which is p naught is equal to E, which is equal to m into dt by d tau, which is equal to m into gamma. Now, the contravariant component p mu transforms like a 4-vector because m and d tau are invariants and the contravariant component dx mu is a 4-vector. The contravariant component p prime mu is equal to lambda mu nu into the contravariant component p nu. From equations 25.25 to 26, we get the relation E square is equal to P square plus M square. And the scalar product of contravariant component P mu with the covariant component P mu written as P square is given by P square is equal to the product of contravariant component P into covariant component of P mu, which is equal to the covariant component G mu nu into the contravariant component P mu into the contravariant component P nu, which is equal to E square minus P square equals M square. Let us now discuss the relativistic kinematics in scattering. We consider two-particle scattering where 1 plus 2 gives 3 plus 4. So, the particles 1, 2, 3, 4 have the four momentas P1 mu, P2 mu, P3 mu and P4 mu, and the corresponding masses are M1, M2, M3, M4 respectively. Now the conservation of energy and momentum gives P1 mu plus P2 mu is equal to P3 mu plus P4 mu. In terms of energy and momenta, we have E1 plus E2 is equal to E3 plus E4. P1 plus P2 is equal to P3 plus P4 and is shown diagrammatically in the figure. The scalar products of contravariant component of Pi mu into the covariant component Pi mu is equal to Pi square and are given by P1 square is equal to M1 square, P2 square is equal to M2 square, P3 square is equal to M3 square and P4 square is equal to M4 square. In order to express scalar products like Pi mu into Pj mu is equal to Pi Pj, where I is not equal to j, we use invariant Mandelstam variables s, t and u defined as s is equal to square of P1 plus P2, which is equal to square of P3 plus P4. T is equal to square of P1 minus P3, which is equal to square of P2 minus P4. U is equal to square of P1 minus P4, which is also equal to square of P2 minus P3. The three variables s, t and u are not independent. In fact, s plus t plus u is equal to square of P1 plus P2 plus square of P1 minus P3 plus square of P1 minus P4, which is equal to 3 times M1 square plus M2 square plus M3 square plus M4 square plus P1 into within the brackets P2 minus P3 minus P4. This is equal to 3 times M1 square plus M2 square plus M3 square plus M4 square plus 2P1 into minus P1. Thus, s plus t plus u is equal to M1 square plus M2 square plus M3 square plus M4 square. We next consider the laboratory frame. In the lab frame, as shown in the figure, we have a particle 1 which is scattered on a target particle 2 which is at rest. In the lab frame, P1 mu is equal to E1 P1, P2 mu is equal to M2 0, P3 mu is equal to E3 P3 and P4 mu is equal to E4 P4. Thus, S is equal to square of P1 plus P2, which is equal to E1 plus M2 whole square minus P1 square, that is M1 square plus M2 square plus 2E1 M2. Thus, E1 is equal to S minus M1 square minus M2 square divided by 2M2. T is equal to square of P1 minus PS and is equal to M1 square plus MS square plus 2P1 PS, which is equal to M1 square plus M3 square minus 2E1 ES plus 2 times modulus of P1 into modulus of P3 into cos theta 1. Now, square of modulus of P1 is equal to E1 square minus M1 square and is equal to the square of S minus M1 square minus M2 square divided by 2M2 minus M1 square, which is equal to lambda, which is a function of S M1 square M2 square divided by 4M2 square, where lambda of xyz is equal to x square plus y square plus z square minus 2xy minus 2xz minus 2yz. U is equal to square of p1 minus p4 and is equal to m1 square plus m4 square minus 2e1 e4 plus 2 times modulus of p1 into modulus of p4 into cos theta 2. We next take on the center of mass frame. It is more convenient to consider a scattering process in the center of mass frame in which the center of mass is at rest and therefore the particles 1 and 2 approach each other with equal and opposite momenta, and after scattering they travel in opposite directions with equal momenta as is shown diagrammatically in the figure. So we have P1 mu plus P2 mu is equal to P3 mu plus P4 mu, where P1 mu is equal to E1 comma P, P2 mu is equal to E1 comma minus P, P3 mu is equal to E1 comma P prime, and P4 mu is equal to E1 comma minus P prime. S is equal to square of P1 plus P2 and is equal to E1 plus E2 whole square, which is equal to E1 plus E2 whole square and is equal to energy ECM square. T is equal to P1 minus P3 whole square and is equal to M1 square plus M3 square minus 2E1 ES plus 2 times modulus of P2 into modulus of P prime into cos theta. Thus T is equal to P2 minus P4 whole square, which is equal to M2 square plus M4 square minus 2E2 E4 plus 2 times modulus of P into modulus of P prime into cos theta. Thus S is equal to E1 square plus E2 square plus 2E1 M2, which is equal to modulus P square plus M1 square plus modulus P square plus M2 square plus 2 times square root of modulus P square plus M1 square into square root of modulus P square plus M2 square, where modulus of P is equal to square root of lambda, which is a function of S M1 square M2 square divided by 2 times square root of S. Modulus of P prime is equal to square root of lambda, which is a function of S M3 square M4 square divided by 2 times square root of S. So E1 is equal to S plus M1 square minus M2 square divided by 2 times square root of S. E2 is equal to S plus M2 square minus M1 square divided by 2 times square root of S. E3 is equal to S plus M3 square minus M4 square divided by 2 times square root of S. E4 is equal to S plus M4 square minus M3 square divided by 2 times square root of S. For the case of elastic scattering, M1 is equal to M3 and M2 is equal to M4. So we have modulus P is equal to modulus of P prime. E1 is equal to E3 and E2 is equal to E4. T is equal to minus 2 into square of mod P into 1 minus cos theta, which is equal to minus 4P cube into sine square theta by 2. T is also the negative of the square of momentum transfer since T is equal to P2 minus P4 whole square, which is equal to minus of P2 minus P4 whole square, which is equal to minus Q square. We will now discuss the relation between scattering angles. Let the particle M1 moves in the laboratory frame along the x-axis with the velocity v1, and M2 is at rest in the laboratory frame with v2 equals 0. In the center of mass frame, let M2 move with the velocity v2 naught. Thus, the center of mass moves with respect to the lab frame with the velocity v2 naught and in the x direction, that is, in the same direction as the initial motion of M1. Thus, by Lorentz transformations given in equation 25.2, we have E10 is equal to gamma 2 into within the brackets E1 minus beta 2 P1. P10 is equal to gamma 2 into within the brackets P1 minus beta 2 E1, We call it as equation 25.45. E20 is equal to gamma 2 E2 and P20 is equal to gamma 2 into minus beta 2 E2. Center of mass frame is defined as P10 into P20 equals 0. Therefore, gamma 2 P1 minus gamma 2 beta 2 E1 minus gamma 2 beta 2 M2 equals 0. Thus, the velocity of the center of mass frame with respect to the laboratory frame is beta 2 equals V2 equals P1 by E1 plus M2. We call it equation 25.46. Now, after scattering, the incident particle 1 has momentum P1 prime, which has components P1x prime, P1y prime in the laboratory frame and P1 naught x prime and P1 naught y prime in the center of mass frame. We have tan theta 1 is equal to P1y prime divided by P1x prime. We call it as equation 25.47. Transforming from center of mass frame to lab frame, we have beta tending to minus beta and is equal to P1x prime is equal to gamma 2 prime into P10x prime plus beta 2 prime into E10 prime. P10y prime. Since P is equal to n gamma V, so we have P10x prime is equal to M1 into V10 prime into gamma 1 prime into cos theta. P10y prime is equal to M1 into V10 prime into gamma 1 prime into sin theta. E10 prime is equal to M1 into gamma 1 prime. Also in the center of mass frame, P10 prime is equal to P20 prime, that is M1 into V10 prime into gamma 1 prime, which is equal to M2 into V20 prime into gamma 2 prime. Beta 2 prime by beta 1 prime is equal to V20 prime by V10 prime, which is equal to M1 by M2 into gamma 1 prime by gamma 2 prime. We thus get tan theta 1 is equal to M1 into V10 prime into gamma 1 prime into sin theta divided by M1 into V10 prime into gamma 1 prime into cos theta plus M1 into gamma 1 prime into beta 2 prime. This is equal to sin theta divided by gamma 2 prime into cos theta plus beta 2 prime by beta 1 prime, which is equal to 1 by gamma 2 prime into sin theta divided by cos theta plus M1 by M2 into gamma 1 prime by gamma 2 prime, which can also be expressed as tan theta 2 is equal to P prime sin theta divided by gamma into P prime cos theta plus V2 into EC, where V2 is given by equation 25.46, where gamma is equal to 1 divided by square root of 1 minus V2 square. So students, let us summarize what we have learned in this module. In special theory of relativity, space and time are considered absolute and constitute coordinates in a 4D Minkowski space. The Lorentz transformations preserve the proper time element ds square equals g tau square equals dt square minus gx square, so that the velocity of light is independent of the inertial frame of reference. The scalar product of four vectors is a Lorentz invariant, whereas the four-vector v mu itself transforms like the coordinates in an inertial coordinate system in Minkowski space. That is, dx prime mu equals lambda mu nu into x nu. V prime mu equals lambda mu nu into v nu. Lambda mu nu equals a matrix with the first row elements being gamma minus gamma beta 0 and 0, second row being minus gamma beta, gamma 0 and 0, third row being 0, 0, 1, 0 and the last row being 0, 0, 0 and 1. Thank you students for your attention.